Section: Introduction. In this section, we explore whether simply naming objects in a scene leads to true understanding. While modern computer vision excels at detecting objects and segmenting images, these methods often fall short in practical applications like robot manipulation and grounded image editing. We recognize that current models treat scenes as static collections of isolated objects, overlooking the vital relationships that give scenes their meaning. We argue that genuine scene understanding requires us to grasp how objects interact and depend on each other within a scene. Inspired by the game Jenga, we introduce a new task: virtually deconstructing scenes by removing objects one at a time, ensuring the scene remains stable, similar to how players remove blocks from a tower. Our task, called Visual Jenga, aims to uncover the relationships between scene elements by exploring which objects can be removed while keeping the scene coherent both physically and geometrically. This approach allows us to assess object dependencies, a crucial aspect of scene understanding that is often neglected in current evaluations. Understanding these dependencies is vital in various practical fields. For example, the ability to remove objects without destabilizing a scene is essential for robotic tasks, and maintaining scene coherence is important for realistic image editing. To tackle the Visual Jenga task, we propose a straightforward, data-driven method that effectively addresses real-world scenes without needing explicit physical reasoning. Our approach employs counterfactual reasoning by asking, what if this object were removed? We focus on the asymmetry in relationships between objects. For instance, a cat on a table relies on the table for support, but the table does not depend on the cat. If we remove the table, the cat needs another support surface to keep the scene stable. Conversely, removing the cat does not destabilize the scene. To quantify this intuition, we use a large image inpainting model to estimate the probabilities of counterfactual images, leveraging existing knowledge of well-formed scenes captured in generative models. Through inpainting, we find that replacing the cat leads to a variety of plausible objects, while inpainting the table consistently yields similar support structures. By averaging these differences, we can determine the order of object removal. In summary, our contributions include 1. The Visual Jenga task, which evaluates object dependencies through sequential removal, and 2. The Counterfactual inpainting approach, a training-free method that quantifies these dependencies using large-scale generative models. We validate our approach with both quantitative evaluations and qualitative scene decompositions. Next, we review related work that has addressed scene understanding in its original context. In the early days of computer vision, the goal was to reason about physical scenes from images. The first PhD thesis in this field focused on analyzing object relationships to enable robots to manipulate simple blocks. However, over the past 60 years, the focus has shifted to object detection and semantic segmentation, often neglecting the deeper understanding of scenes. We also highlight the work of psychologist Irving Biederman, who argued that human scene interpretation involves more than just listing objects. He identified essential physical and geometric relationships that must be satisfied for a scene to be coherent. Building on this, researchers have developed systems that incorporate these constraints, leading to layered scene representations and multi-layer reasoning. Recently, there has been a resurgence of interest in physics-aware scene understanding, revisiting concepts from the original blocks world in both synthetic and real-world contexts. Section Summary. In this section, we introduce the Visual Jenga task, which evaluates scene understanding by sequentially removing objects to explore their dependencies and interactions, inspired by counterfactual reasoning. We also discuss the historical context of scene understanding in computer vision, highlighting the shift from analyzing object relationships to focusing primarily on object detection and segmentation. Section: Counterfactual spatial reasoning. In this section, we explore counterfactual spatial reasoning, which involves identifying causal relationships from observations. This has been a challenge in the causal inference field. In computer vision, Lopez Paz and colleagues examined how one object can cause the presence of another using causal measures. Goyle and others utilized visual changes to clarify model decisions by demonstrating how altering specific image elements affects predictions. Besserve and their team introduced counterfactual interventions to identify components in generative networks, allowing for targeted image editing and causal analysis. Joe and colleagues studied how people respond to simulated block towers to understand physical support relationships. We build on these principles, applying them to complex real-world data with large pre-trained generative models. While observational data often only shows statistical co-occurrences, large models trained on images and videos exhibit strong counterfactual modeling abilities through various prompts and classifications. These models understand a scene's visual aspects, such as geometry and lighting, and can identify object segmentation effectively. Next, we discuss object dependencies and scene graphs. Some research represents scenes as graphs of relationships between objects. For instance, Visual Memex viewed each object as a node connected by edges representing visual similarities and spatial co-occurrences. Visual Genome expanded this concept using a large crowdsourced scene graph, leading to further studies. However, these approaches mainly focus on 2D relationships and overlook geometric or physical interactions. Other methods break images into object-centric components but fail to account for interactions and support relations. Regarding object removal, previous studies have mainly assessed the visual quality of removing, inserting, and inpainting objects. Existing benchmarks evaluate inpainting quality and object removal performance, but we note that no benchmark specifically examines structural dependencies between objects or validates the correctness of object removal sequences in a scene. We introduce the Visual Jenga task, which tests scene understanding beyond mere observation by requiring an algorithm to simulate actions on a scene. Given an image, the algorithm must generate a sequence of images that removes one object at a time while keeping the scene stable. Successfully removing objects without destabilizing the scene indicates an understanding of object dependencies. We propose a straightforward, training-free method for the Visual Jenga task that determines the order of removal based on object co-occurrence, without needing explicit physical reasoning. We illustrate dependency as conditional probabilities. For example, searching for cup online yields many images of tables, while searching for table rarely shows cups. This asymmetry highlights the dependencies between objects in a scene. We denote a cup as A and a table as B. The relationship shows that the probability of finding a cup given a table is very low, while the probability of finding a table given a cup is very high. This asymmetry reveals not just the existence of dependencies but also their direction, extending Reichenbach's principle of common cause. Our method compares the probabilities of a given B and B given A, which is more practical than traditional causation theories that require more complex reasoning. In our counterfactual inpainting method, we generalize to scenes with multiple objects. We replace the conditional probability notation with a more complete version that includes the rest of the scene. We start with the understanding that large generative models capture the distribution of images. For a specific image containing objects A and B, we can estimate the conditional probability by masking out one object and using the generative model to fill in the masked area based on the remaining image. We can similarly obtain the probability for object B by comparing these probabilities. We can infer object dependencies solely from co-occurrence statistics. Section Summary. In this section, we explore counterfactual spatial reasoning and its application in understanding causal relationships among objects in complex scenes, leveraging large pre-trained generative models to infer object dependencies and scene stability through visual interventions. We also introduce a training-free approach to the Visual Jenga task, which evaluates scene understanding by simulating object removal while maintaining coherence, and we propose a method for estimating object dependencies using conditional probabilities derived from co-occurrence statistics. Section: Practical Details. In this section, we outline practical details to enhance our algorithm. We need to clarify how to 1. Obtain object masks, 2. Reliably compute conditional probabilities for inpainted images, and 3. decide which object to remove first. Our choices are illustrated in the accompanying figures, but we acknowledge that these decisions may evolve as technology advances. 1. For obtaining object masks, we utilize existing models. We start by extracting object coordinates using MOLMO, which we then use as prompts for SAM2 to generate segmentation maps without class labels. 2. To ensure reliable conditional probabilities, we recognize that directly extracting likelihoods from image diffusion models can be unreliable. This is due to the noise in the probabilities for specific objects and the fact that diffusion models aren't designed for likelihood scoring. Instead of focusing on a single object, we evaluate a semantic class of objects and measure the peakness of the distribution of probabilities. We refer to this as the diversity score of an object. To calculate this, we gather multiple inpaintings of the object and assess their semantic diversity using features from Clip and Dino. While using either feature alone is effective, combining both yields more robust results. 3. When it comes to removing objects, we prioritize the one with the highest diversity score first, using an object removal tool like Adobe Firefly. If a new object appears after removal, we rerun the pipeline to include it in the ranking. For evaluation, we generate a series of images, allowing for human visual inspection as a natural assessment method. We also conduct automatic quantitative evaluations, which include 3 components: pairwise object ordering, complete scene decomposition, and comparisons to simple heuristics. In pairwise object ordering, we automate the assessment of which of 2 objects should be removed first based on physical constraints. We created 2 test sets: the NYU Depth V2 dataset, which provided a substantial number of comparisons, and a more challenging hard parse dataset, which we curated from internet images with complex object dependencies. Our method achieved a high accuracy rate in both datasets. For full scene decomposition, we recognize that while pairwise comparisons are straightforward, they don't fully capture the Visual Jenga task. Therefore, we conduct qualitative evaluations of complete scene decompositions, requiring human evaluators to assess the plausibility and coherence of the sequences. Our method successfully decomposed a significant number of scenes, demonstrating its effectiveness in various complex scenarios. Section Summary. In this section, we outline practical steps for our algorithm, including obtaining object masks using existing models, computing reliable conditional probabilities through diversity scores, and prioritizing object removal based on these scores. We also describe our evaluation methods, which include both qualitative assessments of scene decompositions and quantitative pairwise object ordering tests, achieving notable accuracy in determining removal sequences. Section: Comparison to simple heuristics. In this section, we compare the performance of 3 simple object ordering strategies on the Visual Jenga task, considering that the visual data we capture can be biased. We can either remove the smallest object in the scene, the topmost object, or the closest object using depth estimation. Our findings, as shown in the relevant tables and figures, indicate that these strategies yield inconsistent results across different datasets. They perform well in simpler scenarios, like NYU V2, but struggle in more complex situations, particularly in challenging datasets such as complete scene decomposition and pairwise hard parse. Our method, however, succeeds in over 70% of cases in complete scene decomposition, while the best heuristic, small to large, only achieves a 43% success rate, and front-to-back performs poorly at 8.9%. Next, we conduct ablation studies on the diversity score, comparing different methods for assessing semantic diversity, including Clip and Dino. Our results show that using both Clip and Dino together significantly improves performance, especially on hard parse, which was not used for hyperparameter selection. We also find that increasing the number of inpainting samples helps capture a better distribution of scene completions, leading to improved performance, although the benefits diminish beyond 8 samples. We defaulted to using 16 samples. In our discussion, we define Visual Jenga as a visual task where both inputs and outputs are images. While a text-based version could be possible, it risks allowing shortcuts that bypass true image understanding. Text outputs often fail to localize objects accurately, as shown by previous research, and can produce plausible answers without visual grounding. For Visual Jenga to effectively evaluate physical understanding, outputs must reflect precise spatial reasoning, which is challenging in a text-only format. We experimented with various large vision language models and tools like Instruct Pix2 Pix and DAL-E for scene decompositions. While these models generated good textual descriptions, the visual results were mostly unusable. Our counterfactual inpainting method shows how generative models capture object support dependencies, but it has limitations, such as being slow and only providing a sequential removal order. Unlike humans, who can consider multiple removal strategies at once, our method relies on specific object detection models, which can fail. We suggest exploring an end-to-end approach that integrates counterfactual reasoning for both object segmentation and scene parsing. Additionally, our method lacks explicit physical reasoning and depends on statistical co-occurrences. Comparing our approach with methods that incorporate physical and causal reasoning could be beneficial, potentially using video generative models as simulators. Finally, Visual Jenga prompts important questions about object granularity, such as whether to define an object as a single sheet of paper or an entire stack. Understanding how generative models represent compositional structure could enhance our insights into object perception and reasoning.